Yes, as Christian mentioned, we now go to gallium nitride, and I would like to widen this perspective actually, and to start with the crystals and the crystal growth really, as to get you some insight how we try to tackle the topic, because we are on the opinion that if you watch finally at reliability of the device, everything comes from the material. So the device is just built on some material. And these four, and also as we are in the part of crystal growers really, I would like to widen your perspective now. Then, so, and for that, I need this illustration where you see really what is the electronic materials that exist in the world, in the watch around. You have your cell phone, you have your computer, you have inverters, you have converters, if we go down here. So you have a lot of electronic devices, but it's like a pyramid which is placed upside down on the tip. So what you start with in order to leverage all this potential is really you start from a material where you have to do a crystal growth. So this is really the source of this widening pyramid balancing on the top. So imagine if you won't have crystal growth of silicon, for example, you won't have your regular world like you used to now. So you have those cell phones, you have no transistors, you have not the world like we have now. But this is something what I would like to raise awareness for you, that really the materials and where it stems from what we have here in our daily life is really something which narrows down to a small community of people and a small community of business where crystal is known. And if you have your device, you're maybe here. And if you do something like electronic boards or circuits, you're here. But it goes like, I don't think that it's even linear than the side walls and such a product. So this is just something for you to keep in mind where you see that everything comes from the material finally. And we have to identify also the barriers if we want to launch a new material into the market, which makes us an obstacle to join a material where we think from a physical point of view, this is a very good material to make it enter into this change into the top. Something like this you can find from the European Research Council, and it's very strategic also. And I can just look at the content. Okay, so by this I would like to put the finger on what we're doing. So we start from the material, we watch at the technology, we manufacture the crystals, we also manufacture the wafers. So you should not oversee if you have a pretty crystal, this is a pretty crystal, it's fine and we find it very nice, but it's no worth if we don't have a wafer because people want to put epitaxy on it. And later if you epitaxy, you go to the packaging, then you have the device, and then you bring it to the end of the lamination. So this is everything that we have to go through for a new material. So maybe the crystals are one like the really key materials for the new centuries, but you have to research along the whole value chain. So for the gallium nitride, what we're looking at, so you have the nitrides, and I would say it's gallium nitride and the aluminum nitride. I cannot touch the aluminum nitride for today for sake of time. But we have to care about material synthesis, we care about the systems, and amongst the synthesis and the technology, you find the crystal growth rate from epitaxy, which you can see here. You find also the devices, even with test devices, giving out new material, or other devices. You find that you have to care about contacts, dielectrics, all this kind of stuff. You have to characterize your material, all the devices and the AP layers, and you learn a lot if you add process simulation. Process simulation can go to any process. And finally, you have to do demonstrators, which can be on various applications. So this is more in detail what we do. So we also have to care about the crystal growth, which is the HVPE process. So if we do HVPE processes, we have to make the full program, which means that you have to care about a machine. So if you don't have a process which grows crystal, you don't have a machine that grows your crystal. So you have to care about the design of the reactor. You have to care about further developing the inner part of the reactors. You have to care about how the crystal really grows. You have to care about what seeds you put and so on. This is really also very, very relevant. And this is something which creates large units. So if you don't want to go to all these large theories, then you better add simulation and digitalization issues or steps where we better learn how to formulate all the things that we find in a physical model and then handle it by digital ways. In the ideal case, you can generate a digital twin. Oh, this is a German-English mix, so I'm sorry. So in the ideal case, you generate a digital twin such that part of it can be run on a digital machine, let's say. So if we then study the technology, we start from the epitaxy and we start from the qualification of the substrate. So we put a substrate, and I think many of you have realized that if you take a gallium nitride substrate and another gallium nitride substrate from another vendor, it behaves different. It's not the same. So it's an individual case, and it's either by a substrate, which is not what you like in epitaxy. So we have to find out what the fundamental differences are, and we'll show you something of this. And it's the same also for gallium nitride on silicon. So if you buy a gallium nitride on silicon from vendor A and vendor B, it's not the same. So you have to also qualify it for your fab and for your process to find out if this is really, if there are adaptations needed, for example, to your process that you later run on such material or not, and what is the issue related to why you need changes. So this is a big part, the characterization, where you really have to see either the materials characterization or the device characterization, and in the ideal case, bind everything together. While we're looking at the gallium nitride, I think I can spin this. You have heard this, and also that we have many applications in order to save time. And there is something which I want to mention anyway. I think you have maybe seen this yesterday also. You know where the gallium nitride and aluminum nitride is located in the band gap versus lattice studies diagram, and it's the same also. I think this you have also seen this very common figure of merit, I would say, or very common quant, where you have the specific on resistance versus the great GaN. And this is the target where we want to go to, the gallium nitride. Here you find the aluminum nitride and even other cap materials. This is something that we are also targeting, but not from today. And then remember that the breakdown field scales with the energy of the diplex. So the aluminum nitride is here, and with the gallium nitride we are playing around here. Let's take this. And I think this is just summarizing what you also have read before from ST. So we are counting on a low on resistance for these materials. We really count for reduced switching losses. This is why we research the material other than silicon carbide. We expect high operation frequencies and less heat generation inside the material, and this will bring you to a large, let's say, a higher power efficiency and the downsizing really of the systems. Can you see one example here? How drastic the downsizing will tell you. One of the advantages, but this is also something that you have to watch out for the devices, is that we don't do chemical doping necessarily. So for the functioning of a lateral device, like you see here, we don't need a chemical doping, I would say. It's not 100% sure, but you don't, if you're going to see about p-type, but in principle, first of all, benefit from the polymerization flattening, which is a big advantage, I would say, because you don't pay with the loss of mobility in chemical doping. And this also brings you to some application field which has not been addressed so much so far, because in chemical doping and we have some, let's say, a vertical device type or a type where you don't rely on the two-dimensional atoms of gas. You may have problems if you apply it under lower temperature. So higher temperature is one issue, but let's watch at the lower temperature. So now we have a lot of questions related to power electronics and low temperatures, or let's say middle market temperatures. But you see that the two-dimensional electron gas is quite a big benefit, because if you compare it to a MOSFET structure, either it's silicon MOSFET or it's a carbide MOSFET or other type of device, you see that with lower temperature, you really deviate strongly in the on resistance. And this is something that you really gain from the concept of a two-gate device, because you cannot just freeze the premise. So this is really a point where the gallium nitride becomes even more interesting for the operations at lower temperatures. But why we are often missing the target? I would say we have a big potential now that we want to have for the gallium nitride, the physical potential, we have the light-barriers, we have polarization going. But why we are not really hitting the physical potential of the material? And this is due to limitations that we face if we really put the material in a heteroarchitectural solution. And here from this plot, there are many plots like this exist, and I just choose one of those. You see that there are vertical power diodes, you have different solutions here, you have silicon carbide and silicon as a reference, you have gallium nitride and silicon, gallium nitride and sapphire, and you have gallium nitride on gallium nitride, which means that your device structure sits on a gallium nitride substrate, on a true bulk gallium nitride substrate. And there you see that these specific on resistance versus breakdown voltage plot that you have seen before, which only monitors the physical expectation, then gets closer to reality. So, which is not the case for any of the other solutions that are normally seen in one nature. So, actually, the theoretical expectations, to my opinion, we don't reach because we have limitations which come from the actual solutions. So the choice of the right substrate is the key. And since I said I would like to widen your perspective, what you really have to look at, you see this illustration here, which any of such boxes is monitoring a point of action that you have to watch it. So you come from the materials, you have to create a seed for the crystal burst. Then you're here, but you have to go through all these line where you say you have a processing of wafers, you process the ingot, you solve the ingot, you have to clean the wafers, this is a big issue, not to oversee, and then you start in the architecture process. So if you're processing the wafers and stitch them and clean them and put them in the box, the people doing epitaxy want to take it out of the box and turbo voltage, it should function. With no issues, no bumps, no whatever, can you make sure in the actual process. So this is cleaning and finishing of the wafers is a big issue, despite everything that comes in the material properties. Then you do the device processing and you have a device, you check the performance and you check reliability. And now how we can understand how this back relates to the crystals. And this is what we are doing, and we're trying to bind everything together in order to better understand how you can leverage the full potential of a new semiconductor materials. And this means that you need an understanding of the device performance from a materials perspective. So here you just see there is no time to go into the wafering, it's an old issue, but here you see what wafering means. You have a crystal, you have to trim the crystal because you need a round wafer. But crystals don't necessarily grow in round, they grow in what shape what they want. So you have a happy shaped crystal, which is hexagonal, then you trim it round, then you need a crystal orientation because the wafer has a final orientation to the surface. Then you have to cut it in slices, you grind it, you clean it, you polish it, and then you try it out in the mix. And then you get a surprise saying, oh, the whole jelly has functions. Then if it doesn't function, you have to go back and to go to slides. This is something that is very important. So the quantity of the substrate that you get out of this chain is really determining also the performance of the device. The need is the change. We will define how good your accuracy can be noticed. So finally, what we do is we try to understand what does not function. So it's easy to say, okay, everything functions, you're happy, but then you're never safe if something happens in between and something fails, that you have understood why it fails. So if you come from the backside, say, I have understood why things fail, then you're on the safer side. So what is really in the heart of the semiconductor demands? This is simple. So you have a substrate, and you can take, and you're researching from literature, you have a substrate and you have a sequence of the epitaxial layers on top that are deposited on the substrate. And what is happening now? So if you consider homoepitaxy or heteroepitaxy, it means that in the case of homoepitaxy, you have a substrate and the epitaxial layer of the same kind. So this means that you have a perfect match, and perfect match means not only structurally but also thermally. So also the CTEs should match. And this is then at the end creating the most perfect match it has. Of course, if you have defects in the substrate, they will emerge in your epitaxial layer as well. If you don't have defects in your substrate, or the lowest number is possible, you have the lowest number is possible in the device epitaxial layer sequence. Whereas if you compare the heteroepitaxy solution, it means that the materials have to be adapted in terms of the lattice match, but also in terms of CE match. So if you heat and cool during the process, you might bend your wafers and so on. And here you see that the atoms need to accommodate for mismatch. So this is why you create mismatch dislocation. So we always have a higher defectious system in heteroepitaxy. And this is what we have in gallium nitride on silicon. Of course, there are benefits for this technology, but this is physical truth. So here you can see another plot for the effects of substrate choice. And you see that, for example, off-state leakage current, which is sketched here, versus total dislocation density, you see that if you put gallium nitride on gallium nitride on sapphire, and gallium nitride on silicon for comparison, and the bare number of dislocation. And I'm not talking about the types of dislocation, whether they count or not. This is the bare total number. And you see that the gallium nitride on gallium nitride really brings down your leakage currents. So you compromise your, let's say, power performance of your device strongly by the substrate that you're using. And here you see just a quick insight. So you see, for example, chorusoluminescence imaging, which is a dark spot counting that you see here. So any of the dark spots stands for place of a dislocation or a bundle of a dislocation. And you see gallium nitride on silicon with around 10 to the 9 orthogonal dislocations, and you see a freestanding gallium nitride crystal 10 to the 5 to 10 to the 6 regular dislocations. And come back, please, what these dislocation structures are doing to those vast. And here you see the plain bare, just one side difference. Let me make a little bit tour to crystal growth. And remember what a real crystal is. So, or the ideal crystal is a strictly geometric, infinite, periodic arrangement of atoms. So, per definition, no defects. If you have defects, whatever they are, you have a real crystal, which is what we have in real physical world. So, no ideal crystal, but real. So, we have to deal with it. And now we have the plan that we say the gallium nitride substrate would be the very best of all. So we want to have a gallium nitride substance. Like, why are we doing this on silicon and we don't have the gallium nitride substrates available in large quantities, in large diameters, and for cheap? And this is the detour I want to make. So you have to think about how we choose a little growth process. So you have a raw material, just something, and you want a crystal with a perfectly ordered lattice. So how can we bring all these atoms in a perfect order? So you have to think about how to mobilize the building blocks of the crystal, which is the atoms. So you can either evaporate, you can melt, or you can solve your material in something. So you have a gas phase, you have a melt solution, or melt, or you have a solution process. And then you condense your crystal out. So I either condense or freeze or deposit. This is a fundamental principle, so no way around this. Yeah. So what is the gallium nitride and what is the aluminum nitride doing? So then you have crystal growth processes which function for meltable materials, which is very classically the silicon. So silicon Shochatzi growth, it's just a silicon melt. And you can pull out these big crystals. Then you have materials that can be evaporated, and you have materials that cannot be evaporated and not be melted. And this is the new corner we have with the gallium nitride, so it can in principle not be melted and not be evaporated. It can be evaporated, but then you have this nitrogen and you have the aluminum and the gallium, and you take the aluminum nitride also into account. And you can imagine very easily that rate pressures are extremely different between a gas, the nitrogen is, and a metal, which has some gas pressure, but it's never the same in the pure case. So what can we do? We choose with the HVPE process a gas phase process, and with the flux growth of the monothermal growth, we choose a solution process. So first of all, I would give you a little insight in HVPE process, gallium nitride, and then quickly in the monothermal process. So the problem is why you cannot melt it and why you cannot so easily evaporate is this diagram where you see it's a temperature versus pressure diagram. So you see that the gallium nitride is dissociating very fast, and it's not a congruent melt nor is it congruent evaporation. So you see that you end up with very high equilibrium oscillations. So you could only melt it and grow it classically under extreme high pressure, which is impractical. It was shown by the community in Poland, but this is very untrue. So you have the classical gas phase process, like KDT, which is not favorable, which could be done for aluminum nitride, but not for gallium nitride. So we choose a chemical mediated gas phase growth, I would say, to keep the gallium nitride in a gas phase by adding fluoride. And this is the HVPE process, which you can see still here for horizontal reactor. There are other reactor types existing, but this is bare principle. So you see that you have some chemical assisted gas phase growth, which means that you add some chloride and you carry the chloride as a gallium chloride to the growth surface. So here you carry the gallium chloride coming from some source to you add the ammonia and you deposit the gallium nitride at the filter, you substrate at the filter. This is the principle. And now you see what happens, how the crystal look. There are different types of crystal existing, including our crystals, which look even also different to the other ones. And I would say the HVPE processes together with the channel processes nowadays are the only processes that are able to produce thick crystals that they can slice in wafers. And you also see that the number of impurities is quite okay. So you're on the order of 19 to 30 and to the 17 with the silicon. So this is quite okay in terms of impurities, and you will see for comparison how their monothermal crystals look like, but you also see that you have many growth issues still. So the crystals are strongly strained because no seeds really exist. So you see that they have uneven growth thickness, so they grow like a hill. So in your slices, the first wafer will be smaller than the second wafer and so, which is often not acceptable. You see that wafers can be done out of this, but you also have cracks, overgrown cracks, all these issues. The dislocation density is 10 to the 6th of 5 times 10 to the 5 for the HVPE gallium nitride crystals. And you see that later on, of course, you have to insert the quantity of the crystals very detailed, because I said you do characterization, you do the growth, you do simulation, you do characterization, you do growth, you do simulation. And then you go through all the grow again and again. And then optimizing your reactor, looking at the material and some scale theories. And here you see, for example, solvents have maximum mapping of over the full volume of the system because we can transmit the crystal in this case. And you see that there are also issues at the edges, in the middle, it's quite okay. And so we have now to address what's happening on the sides of the crystals, for example. But does it really help? This is the question. Now we say the theoretical expectation, we do gamma nitride substrates, and we just change. Imagine the vision is we have large 300 millimeter gallium nitride substrates for cheap. Is it really helping so far? So far, yes and no. You see here, for example, this is in a collaboration with the colleagues from FDH in Berlin, and they measured power transistors made on gallium nitride substrates. You see here N-type gallium nitride substrates, and you see it's just a plot of the median here and the gate source voltage, and you see that the blue and the green and the red curve, this is HDPE material, the green and the red, and the monothermal material is blue. But in fact, it's all gallium nitride, pure gallium nitride substrates. But they behave differently, and it's not slightly different, it's a remarkable difference. So it's a C-equivalent. So what is causing these differences, although we have gallium nitride as a substrate? So all the substrates are different in terms of dislocation density, Ofcad values, and structural homogeneity. This is what I would like to show you in the next transparency properly. So it may help and may not help. Why is the monothermal material different at all? So you see that in the HDPE material, we have many issues, like the diameter is getting smaller, you create cracks, you can have growth kits. You can have nice substrates, but they are highly strained, and then you touch it and then they break. And then the issue is that for the HDPE material, you start, for example, on a CD because you want to get a larger light and use 4-inch, and there's no native 4-inch gallium nitride existing. So you start on a sapphire, you seed it on a sapphire, and you have a HDPE gallium nitride thick crystal on top of it, up to 10 millimeters, and it makes the whole thing grow. So also the whole crystal, even if it looks flat, is highly strained inside, because the lattice is strained, and then if you're touching it, it may break, if you heat it, it may break, if you wait for it, it may break. So the strain has to go away, and what the strain is really doing to the lattice, oh, then they mix up, I'm sorry, they should be before. But let's compare how strained the monothermal crystals are and what is the difference with the monothermal crystals. So the most severe issue with the gallium nitride from HDPE is the throwing and the strain of the crystals. And the monothermal growth process is a solution growth process. So it means like you dip the crystal seeds into a solution which contain all the material that you want to deposit on the seed. It's like putting a seed in a solution of sugar, and then you grow the sugar crystal. So it's a comparison. And this is very much comparable to hydrothermal flux of quartz. So you may know that the quartz crystals are grown in large quantities and tons of crystals and big ornaments. This is the same. The difference is that the supercritical ammonia that you're using is extremely corrosive, and it's extremely delicate to handle it under higher pressures and temperatures that are, of course, not so high, but to handle this high corrosivity and also to avoid that everything is decomposing fast as you have a lot of hydrogen which goes everywhere. This is also something that you don't want. So it's a difficult technology, still under development, I would say, even though the colleagues from Poland, for example, have quite good solutions to handle this. But it's still not clear whether you can really use it to, like you use it for quartz issues, some good cobalt. The crystals, of course, look nice. You also have the hexagonal, like you've seen before. So also wafering is you have the trinity crystals, and you're losing air that where you have to downsize due to doctrine. And you see that the number of dislocations can be, the number of impurities can be quite high in the crystals. So the number of impurities is an issue to the gallium nitride coming from the thermal processes. Of course, the bodies are still strained because you have things like breakage and so, but you don't have things like through holes, big repeats, and the total strain compared to the HEP are bowling is less. And this is what you see here in a comparison. So what would you really need to launch a technology would be a larger crystal on decent costs. So if you compare both of these, you have from a monochrome and from HEPE substrates with different properties. And this is why these differences in the device performance system here, even though you have gallium nitride named substrates. The threading dislocation density or total dislocation density is much less for the monochrome. It's by 2 orders of magnitude, I would say, or 1 to 2 orders of magnitude. The diameter is a bigger issue than HEP. So the crystal growth technology must be further advanced, and this is just a quick sketch how we do this. Here you see a vertical setup now, and this is what I have said before. We are adding now numerical modeling and digitalization in order to better control the crystal growth process. This is a big issue for a monochrome. For the HEPE reactor, this is easier to do than for the monochrome process, because for that monochrome process, you have a closed system, you can measure nothing, and just not look inside some system light box and see the more. So here you see, for example, a continuous bow curve over the radius thickness, which reflects the process time, so the growing thickness of the layer. And you see that the crystal starts bowing. And with a model how the crystal really grows from the nice fluxes and from the temperature field that you implement here in the physical model, you can simulate such curves and better understand really what your process is generating coming intuitively reacts, and you eventually understand the consequences of the substrate properties failure and you better understand the runs process. This is what I have touched before shortly. What is the boat lattice doing really? Why is this relevant today? Because you see, imagine that your crystal bindings are bound in the crystal, and now you cut a wafer out of this, you will end up with something like this, where the contact angle versus the surface is uneven, or not the same all over the wafer area. And what you want in epitaxy is a layer by layer growth. So you want really to determine the terrace length and the terrace height of a step through growth. What you don't want is three-dimensional nucleation to the one cycle chain, because I can show you what this is doing. So we really have to carefully control the growth mode in epitaxy. And this variation of off-cut really is making a big issue. So here you see this binary step flow, which is an AFM picture. This is what you want really, and this is what you have. So you grow a hand structure, an easy one on top of this, and you say now you have to adjust your epitaxial process, and you have to choose 3-5 ratios, mole fraction, velocity of gases, and so on. You have to choose aluminum and gallium you have to choose the mixture for the alloy barrier and so on. And you have to choose a GME outflow. And then you see, okay, you have an uneven offcut. And the uneven offcut also means that you cannot control the carriage lengths for the aluminum and the gallium in the same way perfectly. So what happens is that the mole fraction that's being included is a function of the offcut angle in your alloy barrier. So the off-cut angle that you have here will at the end create, let's say, oscillations in composition of the aluminum gallium over there. And this can be up to 5% even, which is what we have seen. And this is really a big issue for the devices, because if you put a device on such a plate and such a place, it will not be the same. What are the differences in terms of off-cut? If you compare the monochrome laser and HEP laser, you can see here is a mapping. So this is the off-cut angle, which can go from 0 to 0.8, so it can be also quite large at the edges, for example. And you also see that it's odd-shaped, so it's not symmetrically that both it's like a wave or like an uneven shape, whereas the monochrome crystals are much better in this sense. So So the issue that we've seen before with this offcut and the uneven, let's say, incorporation of the atoms into the alloy barrier layers, this is less of an issue in the morphosomal material. And this is where we think, you have seen this before, where these differences may come from. So does homoimpedance really help? Yes, it helps. But it helps the best if you had substrate of electrons, which is not the case for electric materials like here. So, and now we are here. How we can now learn what the device performance is. So I said we have to go through all the thing, then we go here, then we go back, and we go back again.
Sure.
And this is what you have seen before. There are many things that you can observe. The question what you're searching for is not so easy to answer. So what you are searching? The total number of dislocations, type of dislocations. You search for offcut angles on the substrate. You search for bowing on the substrate. What will really define the performance of your material? So you have to maybe put it in categories, say what is causing catastrophic failure, something different that causes compared to degradation or long-term degradation. And the easiest thing is to look at dislocations. It's not easy, I can tell you, but let's go through it a little bit. And what we're searching for, I would like to put the finger on this, is a matter of definition. So what you're searching for means, you see this in a plot here as an example. If you have an optical device and you say, okay, I want a wavelength which is like 280 nanometer, you're completely fine if you have that to deny dislocation. When you say, okay, I have some output power or I have some EQE that I want, and with a 10 to the 10 or 10 to the 9 dislocation size they come. If you want a higher performance on your device, then it's getting an issue. So if you say, okay, now I want a UVC LED and I want, let's say, 220 nanometer or 230 nanometer, and then you see all the curves drop down drastically, which means that the output of your device, like you want, like shining light out of it, so you want a lot, extract a lot of photons out of your device, then it won't function so nicely anymore because you have a high number of dislocations. Yeah. So remind yourself, if you're asking the question, what I'm searching for, what you're searching for is a matter of definition. What is relevant for you? Is it relevant for my device to have the utmost small number of dislocations? Or can I be happy with this, then I optimize technology? Or do I need a really high-performing device? Then you have to go on this side. I show you just some examples quickly. We have made, together with colleagues from, this is not Soitec, Belgium, it was ECSEL JU before. We made some devices which were transistor structures, and we categorized them in the red ones and in the green ones. We call them the hot ones and failed ones. And now the question was why we have these differences. So what is really causing the devices to fail the test, such that you have 850 volt breakdown voltage and you have something below, and the below is even varying. So we investigated, we suspected the property of the insulating buffer underneath this. And we were expecting that there are changes in the insulation buffer. And what we found, you have seen the picture of the gallium nitride before, where we have seen the dark spots. You may remember, so you have in the gallium nitride and silicon many of such dark spots. And these dislocations become really close together. So what you find, if you make photoluminescence, you find that there can be, so we observe the near-band emission, we observe the blue luminescence, and we make differential pictures, and the blue luminescence can associate to the carbon protein. So what you see is then that if you imagine that this is a dislocation, what you see is that around the dislocation, carbon content is let's say, getting gathered to the dislocation. So the carbon moves to the dislocations just inside the strength field of the dislocation. Of course, there is some distance that they can travel. They cannot travel any distance they want. So if they are close enough, they are being caught by the dislocation. And what you create in the insulating buffer is around the dislocations are like an N-type conductive zone, so N-type well. And this is really causing leakage. So and if you can measure this also in sizes of such spots, and compare it to theoretical sizes of strength fields, and then you find that even between two dislocations, the carbon depleted region is even more depleted, so it's getting even more irritant. So imagine that you need an insulating buffer, and you create some depleting of your compensating dopant, and then you find that you get this region more productive than in the vicinity. And this is causing actually the result that you had these devices fail, so they have more dislocations that are catching the carbon, whereas such green devices don't find the depletion zones. This is another example if you expect your nucleation to be difficult. So nucleation is a very critical issue because it defines everything that is on top. So it's the lowest layer directly on the substrate, so with ice only halfway to your device potentially will be grown. And here we did the same experiment. So you do a device, of course you have to do some sort of device where you can access the critical regions that you want to measure. And you see a breakdown curve here, and you see also failure devices or press devices. You can name this like you want. So you say, okay, this is lower to 500, but it's maybe not the most nice curve, but at least such devices survive this high voltage, whereas those devices did not. So we just named them sample A and B. And now we did an experiment with a conductive ASN measurement. So you have this structure here, and you measure with the ASN tips from the top, and you make a potential between the ASN tip and the backside of the substrate. And now you scan along your surface in a small area, and you see all such spots where the ASN tip is measuring continuous leakage current, so measuring the current through the structure. Now the question is, how deep does that go? It goes until here, so what you're really monitoring is the leakage of the barriers. And you see that there are differences. You have many leakage spots here, whereas you have less leakage spots here. So now the question was, okay, why do we have so many leakage spots, but this should be blue, but they are surviving the higher breakdown. And here we have less leakage spots, but this is counterintuitive because those were the same ones. And now we look more deeply into the structure, and we saw that through the structure there were some V-pits. And now the question is, how deep are such V-pits and what they are really doing? So what you find is that at such places, and it's called a special preparation that you have to do. So in this case, we have a wedge type sample that we produce where you can do cathodoluminescence and conductive ASN at the same place. And you see here a CL image. When you see all these places, you see a color-coded image with intensity, and you see the leakage current at the same places. Those are all the same places that are marked here. And now we sliced it, and we saw in many SEM pictures, so I won't show all of these, we see that there were at the edges little V-pits, and this is a function of the quality of the nucleation layer. And these V-pits are collecting impurity elements or dopants. And the content where you see here of such a V-pit is different compared to the neighborhood. And this is making a different electrical property very locally. And this is why you find this such leakage spots. And now you count the number of V-pits underneath a structure, and you see that then the red ones and the blue ones, the sample A and U, which has different. And the number of the V-grids you can associate to the mean of the multiple breakdown voltage. And then you see that such V-grids, if they exist and they are initiated in the nucleation layer, will provocate the early breakdown of the substrate units. But now we have thought about investigating early breakdown issues, and before we have leakage issues under the gate. So it's different. This is why I said you have to make a decision what you are searching for, first of all. So if you want to really investigate such things, it's a very complex workflow. So you have a virgin material that has grown from stone leakage taxi, you investigate this. Then you do a processing, and then you make decisions and say, okay, I want to measure such places because they are relevant. Good. And then you end up as another processing level, I would say, and then you have to define what can I characterize and measure at such places. And then you get devices that you eventually can directly measure related to the electrical performance and what's going on in the material. So it's the workflow you have to define for what you're really measuring is very relevant, because this only gives you the real idea whether what you are measuring is related to what property of the device really, and this is important. So finally, let's wrap it up. I would say the YESvGaN materials, the gallium nitride and aluminum nitride, are probably one of the most important classes of new semiconductors to silicon. I won't say that the silicon carbide is not nice, but the silicon carbide and gallium nitride and aluminum nitride have different places where they can act to. But before you have a semiconductor, a wafer, you need the crystal. No device without first starting with a crystal. And this means that you have to go to technology to grow a semiconductor crystal. You need the wafering technology available, which actually fabricate the wafers. And then you can do it with Etsy. And then you go back and investigate what properties of the wafers are in the sheet material that Etsy or not. So the nitride crystal process is developing fast, but by no means mature. So far we cannot offer large gallium nitride crystal. It goes up to 4-inch, and they're more and more appealing by patents. And they have all the issues that I mentioned. So what is the takeaway message? I would say the material development is a key topic for the stable technology. Because you saw the PowerElec, remember, all the technology comes down and again, for the tip of the fingers, wirings and material. So you have to deal with the materials questions, and you have to grow the crystal, and they still determine how much your device is, and you have to go into circles to extra. So the availability of the substrates and the respective crystal growth to your is a key point for the launch of the technologies. And that's it. And of course, we get from the end. And of course, I'm not doing the things alone, because I have all these co-workers in my back. And they are all making my ideas reality. Thank you for your attention.